Machine learning is just a field of artificial intelligence that enables computers to learn from data and make predictions without being explicitly programmed. By saying explicitly programmed, I mean that the computer is given data patterns, and of course, it's from those data patterns that it makes basics and makes conclusions depending on the data that has been given to it. And then you have various types. Of course, you have supervised and unsupervised, but for this case, we shall be talking about two. And we know there are three after adding reinforcement, but then for now, we shall be talking about two: supervised and unsupervised. Machine learning has various applications. We have image recognition, natural language processing, which is NLP in simple terms, but then it can also be used in various fields like health, whereby it can be used in diagnosis, predictive analytics, for example, weather forecasts to predict different weather in different places. We shall now be talking about traditional programming and machine learning. Why is there need for machine learning? Basically, before you are doing traditional programming, whereby we first analyze the problem, then after analyzing the problem, we come up with certain rules, which is hard code. Then after that, we analyze the code and see if there are any errors. If there are any errors, then we go back to analyzing the problem and see how can we resolve the errors. If not, then we launch the program. But for machine learning, of course, this one involves algorithms. If it involves algorithms, it means that we have to first analyze the problem. Then after analyze the problem, we select a certain algorithm of which we shall train it. After training algorithm, we shall then check for any errors, depending on the output has given us. If there are any errors, we go back and train it to analyze the problem again. If not, then we launch the program. After that, we shall be talking again about machine learning like types in details. Supervised machine learning. This is a type of machine learning that uses training data. What do I mean by labeled data? What do I mean by labeled data? Labeled data is whereby we give an ML algorithm, we give it the input and output, and it makes conclusions, it makes patterns depending on the input, and then the decisions depending on the output. That's what I mean by supervised. And of course, it has various algorithms associated with that. Here, I just said problems, but of course, there are also problems. Classification problem and the regression problem. Classification problem is whereby the target value is categorical. For example, you can say animals. Animals, animals can be a dog, it can be a cow, but animals, it's a category. Or you can say it's either 1 or 0, binary digits, you understand? And then regression, which is continuous data. Continuous data, of course, we have temperature, those measures which are continuous, temperature, voltage, all that stuff. Then as supervised data is where a model is given without any labels, just given inputs, and it makes its own conclusions, makes its own patterns depending on the inputs, doesn't have the outputs. For this case, the algorithms we have associated an anomaly detection. Clustering is whereby we group those with similar characteristics together, and then like for Netflix, of course, we've been knowing these certain individuals watch these kind of preferences, watch these kind of movies. So it's from that basics that we base on to give the clustering, because we know that these individuals watch this type of movies. And then anomaly detection, of course, for here, we take the opposite of clustering, whereby we look at those distinct features, which those guys, other guys don't have. For example, in credit card fraud detection, of course, we see that pattern whereby it diverges from a normal pattern. Of course, we know it's some kind of, fraud. And then next, we shall be talking about, feature scaling. Feature scaling basically has two things we shall be talking about: the process of normalizing and standardizing. We shall be having normalized data and standardized data. Normalized data is whereby the range of these two numbers is of these values, either 1 and -1. And then standardized, this is basically a normal probability standardization, whereby I have the mean and the standard deviation. Of course, the mean should be 0 and standard deviation should be 1. Types of feature scale have min, max, and standard scalar. Of course, it has they also have their own formulas. Advantages, you can see you have various advantages, and we know ML algorithms understand basically numbers, so it's because of this feature scaling that we shall be giving them numbers. And then when we do scaling, when calculating the distance and the neural networks. because these things basically contain numbers, and of course, in feature scaling, you'll be dealing with numbers basically. So we are having the ML algorithm. What should it be having? It should be having a reduction model, it should be having a cost function and optimizer function. These are three basic things be having. Then, if I'm talking about a prediction model is just a function that makes predictions based on the input data. It has its function. The function is y x1, y1 x1 plus that up to yn xn. The y is the weight coefficient, and then the x the input, plus b. The b is the bias. And then the cost function, of course, the cost function measures the error between the predicted values of y with the power symbol is the predicted value, and then the actual value of y from the training data. The goal is to minimize this function to improve the efficiency from the predictions. This is because it bases on the mean squared error. The formula is there. It's self-explanatory. And then optimizer function, of course, adjusts the parameters of the prediction module. Depending on the weight and the biases B and W, like I said before. Then linear regression, of course, like the name sounds, linear regression is so about something like a straight line. This is the equation of a straight line, y equals mx plus b. It just shows the relationship between dependent variable y and one or more independent variable x. You just compare the two and come up with a final conclusion depending on whether it's linear or not linear. Of course, like I've said, we have to draw that line of best fit. Line of best fit is like we were doing in physics sometime back. You plot your data points and then get a line that strikes through, process almost all the data points from in between. Then logistics also like linear, but for it uses a sigmoid function, which causes curves like you're seeing on the graph for logistic regression. Then models, of course, a model is a representation of some phenomena or a representation of non-math stats. We have two types, deterministic and probabilistic. Deterministic has no randomness. Probabilistic has randomness, like some chance feeling. Then deterministic hypothesizes exact relationships and suitable when prediction error is very negligible. Then for probabilistic, like it's some sort of probability. Deterministic and random error. In math, we're adding some error. That's where it comes from. Then types of probabilistic, there are three. You have regression and correlation, but the others, that's the third one. Others, there are very many, so that's why we group them into others, but there are basically two. Regression, one independent variable, one dependent variable, and one exploratory variable, which is some sort of independent variable. Then correlation measures strength or direction of a linear relation between two variables. KNN, this is whereby you get a data point like P, which is the target point, then you select its neighbors depending on the distance that is close to them. If a distance is very far, then you negate that. But if the distance between that data point, that class, and the target point is very less, then you consider that. And group them in an increasing order to get the class to be having the best spot. Of course, that's what we both on. And then the implementation, of course, the basically three steps. You catch the distance between the test point and the training points. Like I said before, I won't repeat this. Then it has various applications. We have text mining, whereby like getting the preferences, the cache memory when you're typing something, and then the suggestions come. That's some sort of text mining, agriculture, finance, in stock markets, of course, hospitals, diagnosis. Then I'll talk about decision trees, whereby it helps to group things, like classifying things and some regression tasks. For example, you can say you are going to organize animals which have far and those which don't have far, animals which fly, those which don't fly. Of course, we base on decision trees to make fine decisions, like if it's greater than A or not, like on this diagram.
Concepts in machine learning, starting off with assembly learning. This just simply means coming up and combining weak models. You can also think of them as learners into one supermodel. Why? To improve accurate predictions and also better performance. Well, the main idea in this is called bootstrapping. How I can talk about bootstrapping, you would think of an original data set in this diagram. Then you carry out sampling with replacement. So what you get in, you also put it back, and then you come up with these samples you can see. But these samples are of the same size, and so the size of one, the first sample is the same for 2 up to B. So in these samples, or you could also think of them as bootstrap samples, since it's sampled with replacement, so there's room for data points appearing multiple times in each subset, and there's also room for subset missing out on some of the data points. Well, next on the line is bagging. Well, bagging, you train models, but this is done parallelly. Yeah, so you train models and you feed them in with this bootstrap sample. Bootstrap samples are really explained using bootstrapping. And then you feed this data into the models trained independently. And then after that, the models come up with their own predictions. And these predictions are fed into the ensemble classifier. And if you are talking about classification, of course, you deal with a majority vote. So I'm assuming if classifier 1 came up with prediction of 1, and then classifier 2 came out with a prediction of 1, up to classifier n, and then we find the majority vote as 1, we would take that as 1 as the final result. Then if it's regression, of course, you take the averaging, you average the predictions of all classifiers. Moving on to the out-of-bag error. As I had earlier said, when you carry out bootstrapping, there is that idea of coming up with a subset that lacks some of these data points. So these data points are known as out-of-bag points. So these are used to test the model's performance in that you carry out out-of-bag evaluation. Yes, out-of-bag evaluation, and you repeat it for most of the models. And this actually helps you achieve a model's performance without even carrying out a separate test set for each module. Then there's random forest algorithm, and this is an application of bagging. This just builds, as you can see, multiple decision trees. And then, as I had earlier said, we use bootstrapping to get these bootstrap samples. Just that in this random forest, don't only necessarily only just use a bootstrap, so also come up with features. And these features are also taken also at random at each split of the trees. And then after that, we come up with the results from each decision tree. As you can see, if it says decision tree 1 takes a result of 1, then decision tree 2 takes a result of 2, and so on and so forth. So we average in classification and come out, rather in regression, we come out with the final result. Then if it's classification, we use majority voting. Yes, so the vote that appears most of the time is what we take as our final result. Then moving on to boosting. So now boosting, unlike bagging that is parallel training of models, boosting for it is sequential training that combines multiple weak models. We usually use trees. The main idea in boosting is that we come up with a sample and then we feed into models sequentially. But then the most thing we are targeting is the misclassified data by the previous model. And this is sent into the next model, let me say. As you see, this is a sample that is done in here. It's said into the classifier, this is the correct data, then misclassified data. So we weight up this misclassified data to take mean more priority to the next classifier, and it focuses on that misclassified data, and also does its own, it also does its own weighting, and then also forwards it to the next model like that. So we deal with misclassified data done by the previous model. So the next model inline focuses more on that misclassified data. So then it's also done sequentially until we find a better actuator of the prediction. There are many various boosting algorithms. They also include adder boost, graduate boosting, and also XBoost. And then I go to the support vector machines. So for support vector machines, these are powerful classifiers in that we come up with a best decision boundary or hyperplane. If that's in 3D, if it's in 2D, then we also think of a line. So this, I will explain using this diagram. These are two features, X and Y, as you can see, and they have two data sets, and we want to classify them using SFVMs. So as you can see, we will take C as our best decision boundary because why? One, it classifies the data separately. That's why there's no misclassification. X, like the X data set here, there's no X data set in this data set. Then the dot data set, there's no, it's not in any X data set. And then why? It also maximizes margin. Well, margin, you could think of it as the distance from the closest data point to the best decision boundary. So when we maximize this margin, this creates more room, for that data that wouldn't be misclassified. So it maximizes the margin. So there's a bigger distance from that closest data point to the hyperplane or base decision boundary. Then there's a technique called the Kennel trick. This one, you saw data can be in many types, can be in linear and nonlinear. But then when we want to use SVM memes to handle nonlinear data, we use the Kennel trick. With the Kennel trick, it helps transform the data into a hyper-dimensional space. And this helps it become linear and separable. And when, of course, it's linear and separable, we can use our support vector machines. So the mode of operation, how the Kennel trick works, we start with the original space, the non-linear data. Then I would think of it like a curved decision boundary. Then the Kennel trick maps the data from this original space to hyperdimensional space, where we come up with now a linear hyperplane. And this linear hyperplane, now we can also use it to separate the data points, where it has a simple formula. And this is a function kx, y. X, y are just the data points in the hyperdimensional space. So it takes the dot product of those two. Then after that, that's the function. Well, there are kernel types. You could think of a polynomial kernel and also others that can also be used in this trick. Then supervised and unsupervised learning. Supervised, we all know that involves training a model using labeled data. Well, input data is paired with the correct data. Why? The goal is to learn the relationship between inputs and outputs, predict new and foreseen data. So let me take an example of input as an image of a cat, then we label it with the output as a cat. So it helps this module to learn from this very data, say that if it sees a new variation of a cat, it doesn't know. It learns from the input output data it was fed on earlier on to come up with the right prediction of this is a cat. But then unsupervised learning for it deals with enabled data. The goal of it is just simply identifying patterns and structures or groups in data without predefined labels, for it doesn't work with labeled data. How it works, the algorithm itself analyzes the data to find the underlying structures. Let me think of any algorithm in supervised each clustering. So it groups customers into clusters based on their buying behaviors, or if it's not only behaving behaviors or how they pay. So it groups data for it. Then clustering is a technique for finding similarity in groups of data, and we call those clusters. It has two types: clustering, partitioning clustering. For it, first of all, you have to have a K value. Then secondly, the data set must be in clusters and it's centroid based. Centroid based, you could think of the data, a subset, or rather a data set. Then a data set, you come up with a center point and then surround the data points that will be around near that data. And then you also come up with a K value. Then hierarchical clustering, for it is, you think of it as nested clustering. If this is my data set 1 and this is my cluster, okay, these are my data points, as you can see, 1, 2, 3, 4. I make up the first cluster 1, 2. This is my first cluster. But then I also come again and come out with another cluster that entangles another cluster n within. So that's 1, 2, 3. And then I also come up with another cluster, which is this. So that's hierarchical clustering. And then you also saw distance functions in clustering, but of course, you're based on similarity and dissimilarity based on different types of data, depending on the domain you're actually interested in with the problem. Let me say if you're handling like numerical data uses the Euclidean and also Manhattan distances as the distance functions. Well, these are the simple formulas of coming up with the Euclidean distance, also the Manhattan distance between two data points. Xi and Xj are just simple data points into the data set. And then this is a function that maps it. That this is a function for the Euclidean distance and also the Manhattan distance. So the Manhattan distance is used when each value is equal to 1, just because it's not in binary. But then for Euclidean distance, takes in a value of the exponential making we want to. Yes, so it takes in 2. And then I move on to the K-means algorithm. Now for the K-means just tries to group similar items in the form of clusters. The number of groups is represented by K. So let me say if there was a data set, like now this one. So I cluster in 1, I cluster in 2, I cluster in 3. So my K value is equal to 3. So that's why you're saying 3 clusters. So it bases on a centroid-based algorithm where each cluster is still with a centroid. So I come up with like let me say one centroid like this. Then I use it to group the nearest data points to it. I come up with this cluster. The same goes for the rest. So why we use K-means, just simply because to minimize the sum of distance between the data point and their clusters, as you can see after applying the K-means. Then the PCA, or the principal component analysis, I want to explain it in the simplest terms. I'm going to use this illustration. So you could think of a fish example like here. It has two variables. Let me talk about height and width. So the two variables, you realize they're dependent on each other. As the height increases, the width of the fish also increases. So they are dependent on each other. So we can deal with these two components just using one simple component, as you can see in the situation B. So you realize that when I draw an orthogonal, as you can see, this first shape, the blue one, it lies that most data points lie along it. So it caters for the main variance in the data. Yes, then this dotted one, the dotted line, it caters for the remaining variation that will not have entangled into this experimenting. So the goal of the PC is to reduce the dimensionality of the data while keeping the information loss minimum. That's why